So you know the name of this course is on cellular automata. So we shall cover several aspects of cellular automata, their applications, etc. But this is the first class. So in this class, we shall revisit some concepts which will be required in our course. So today, I'm going to discuss function composition and parallel map. So first, let us discuss the relation and function. So to define relation, we consider two sets. Say two sets D and C, and relation is actually an association between the elements of D and C. So to define it mathematically, let us first discuss about Cartesian product of two sets. So Cartesian product of these two sets D and C is actually nothing but all possible ordered pairs, right? So we normally write in this fashion: D cross C. This cross indicates Cartesian product, and there's a definition. So it's the ordered pair A B. So A comes from the first set D, and B from the second set C. And so mathematically, we can say that R is subset of D cross C. See how I defined it is association between elements of D and C, right? So I'm taking some elements of D and some elements of C. So I'm getting one association. So it becomes a subset of D cross C, where D cross C is association of all elements actually, or set of all ordered pairs. So R is a subset of D cross C. Take an example. Say capital D equal to ABC and capital C equal to this one, 1 hash 2 5 and star. Now what is D cross C? D cross C is this one. See, you see here, you can see here that D cross C starts with A comma 1. So A is from set D, 1 is from set D, from set C. So next is A comma hash. A is taken from D and then hash from C. In this way, A comma 2, A comma 5, A comma star means A is one element of D. For that D, for that element, I have taken all possible options from C. So this is the first line, then second line B1, B hash, B2, B5, and B star. So in this way, I can get D cross C. Observe that here, I've noted down all possible ordered pairs which I can get out of from this D and C. Let us consider R is this. So I've taken a subset of this one. Any subset I can take. So it's one subset I have taken. So D is R is say A comma 1, then A comma star, and C comma hash. So this is a subset of D cross C. So this R can be a relation. So we call this R is a relation. Let us see this thing pictorially. Suppose this is the set of D. Normally we represent this kind of we represent this relation, function, etc. using this kind of diagram. Suppose this is our D and this is our C. And so when we discuss relation, function, etc., we give name these two sets. So D is called domain and the C is called codomain. And now if R is this, as I've defined above, that R is A comma 1, A comma star, C comma hash, that I can represent this fashion. So what this line indicates, that A and 1 they're associated, and A and star they're associated. So I put another line, and so C and hash they're associated. So this kind of diagram we generally use to represent pictorially the relation, right? So it gives a better picture that how the elements of domain and codomain they're related, right? So question is, you can get several kind of R, several subsets of D and C, right? So for each subset, I can get each relation. So therefore, when D and C they are given, for that D and C, I can get D cross C, and for that D cross C, I can get a number of subsets. Each subset is a relation. So for D and C, we can define a number of relations. Okay, so now function. Actually, function is a relation, but in case of function, we put some constant. For the constant is each element of D associated with exactly one element of C. In the previous case, when we are defined relation, this kind of constant was not there. But here I am putting this constant. I'm taking an element D, taking an element of D, and that element is associated with exactly one element of C. So let f be a function from D to C. This is the notation, these are the words we use. F is a function from D to C, and we represent it in this fashion. Say F colon, then D, then right arrow, C. This is the way of declaring a function. So what does it say? So then from the above definition I get, for all x or for all x in D, I can get a fx. I can get a fx, and that is part of C, obviously. Okay, which was not the case for relation. For some x, I cannot get Rx. Second is, for all x, if y1 equal to fx and y2 equal to fx, then it necessarily implies that y1 equal to y2. It means for x, I can get exactly one element in C. So this is the meaning. So therefore, this R is a relation, but not a function. Why not a function? Two reasons. For first condition is violated. Both the conditions are violated, in fact. So first condition is saying that for all x in D, fx is to C. But here B is in D, but for B, I cannot get any element in C. Right? And for second element, for the second point, it is saying it's a uniqueness. So y1 equal to fx, then y2 equal to fx, then y1 equal to y2. That is also violated because from A is associated with 1 as well as A is associated with star. So both the conditions are violated. So this is not a function, but a relation. So if I want to design a function using these two sets, let us add this one. Let us make this association B with 5, and let us cross this one. Say A to star. So suppose I am omitting that one. So then what I get? I get this kind of set: A to 1, B to 5, and C to hash. So this is a function. So both the conditions are respected here. You can see. So this is a function. So what I get from this, an obvious conclusion is all relations are not function, but all functions are relations. Right? So all functions are relations, but the reverse is not true. In literature, sometimes we call function, sometimes we name function as map. In fact, in set theory, a map or mapping, is a more common term. But historically, the term function was used, much before the set theory, the modern set theory. So we love to use function here. So in this course also, we shall use two terms, function and map. So they have same meaning. Okay, relation and mapping, or relation and map, function, and relation and function, the same meaning actually. Function is equivalent to map here. So therefore, this small f is a function or a map. Now let us define this one. Say f of d. So D is the domain, as we have defined. There is a set which is named as domain. So, sorry. So f of D is defined in this way. Say f of x for each x of D. So therefore, if I put f of D, I'll get a function. I'll get a set, and obviously this set FD is subset of C. It has to be. It has to be. So we call this FD as range of F. So these two terms are used, codomain and range. Range is subset of codomain in general. Subset of codomain always. Sometimes range is equal to codomain, but generally range is subset of codomain, codomain set. Here, so FDs for this particular example, FDs 1, 5, and hash. Now, function type. So, functions we have defined, but there are some special types of functions, and we have much interest on these special types. In this course also, we shall deal with these special types of functions. So, they are known as injective and surjective. We shall define one by one. So injective function is actually one-to-one function. So both the names are used, simultaneously. Injective and one-to-one. So same meaning. So one-to-one name, more appealing, because from this name we understand what it wants to mean, right? So it defines this fashion: for all x, all y in t, if fx equal to fy, it necessarily implies x equal to y. Okay, what does it mean? Meaning is given example, then it will be clear. The example I have given here, given in the last case, there is an example of injective function. Okay, it may so happen b is also associated with 1. There's a problem, but if that happens, then that function cannot be injective. But here you can see for A, B, C, I can get unique elements in codomain. Say 1, 5, and hash. Right. So this is an example of injective function or one-to-one. You understand the meaning of one-to-one here. So this is another example of injective function. Suppose if x equal to x plus 1, x is any natural number, so 0, 1, 2, 3, etc. So here natural number, by natural number we mean here a set of natural numbers, so 0, 1, 2, 3, 4, etc. Generally, while we define this natural number, we don't include 0, but here we include 0. We shall include 0 instead of naturals. So set of naturals, this n is set of naturals, is 0, 1 to infinite set. That set, if fx is equal to x plus 1, then that is injective, right? Because for each x, so x equal to 1, then fx equal to x equal to 3, fx equal to 4, in this way. Okay, so you'll get a unique mapping, unique association. So this is injective function. Now surjective function, surjective function, also named as onto function. So again, onto the name onto is more appealing. So, uh, so what does it mean? Range is equal to codomain. If range and codomain, these two sets are same, then we call the function as surjective. So we have defined in this fashion. Here say domain is ABC, but codomain is say only 1 and 2. These two elements are there. Okay. So then the function I have defined here, this is a surjective function. Note that this function is not injective, right? This function is not injective. Why? Because B and C, for FB as well as FC, they are same actually, both are 2. Now, another special type of function is called bijective function, which are very interesting and are of our interest. So a function is bijective if it is injective as well as surjective. I mean, if both the conditions, injectivity as well as surjectivity, is satisfied, then you call the function as bijective. Exercise. So I'm giving an exercise here. So test bijectivity of, so fx equal to x plus 1, where x is in n. So test whether it is bijective or not. See, I have already said that fx equal to x plus 1, this function is a injective function. So here you have to test whether it is surjective or not. Okay, so if it is surjective, then it will be bijective, otherwise not. Now same function, but fx equal to x plus 1, but here I have defined x in z. Z means set of integers. So n does not include negative numbers, minus 1, minus 2. They are not included in set of naturals, but z includes all integers, positive, 0, positive, and negative integer. So obviously z is also an infinite set. But the question is here whether this f is bijective or not. So here you have to test its injectivity as well as surjectivity. Now, when a function is bijective, then we can get an interesting property as inverse. So if a function is bijective, say f is bijective function here, then I can get inverse of f. So we write generally inverse is f to the power minus 1. This is the traditional way of representing inverse function. And here, so sorry, so f was from d to c. Now here inverse is from c to d. Try to imagine. So I don't have figure here. Say for each element of d, for f, in case of f, when it is bijective, for each element of d, I can get a unique element in C. And all the elements of C, they're covered. So therefore, I can obviously define a function, say from C to D, and C to D is say the reverse way. Okay, so the A sorry, so reverse way is say so if y equal to fx, then f inverse of y will be equal to x. This is the definition. Okay, so f is bijective function. So if so y equal to fx, if it is given, then for the inverse, if inverse of y, I'll get x. So in your school level, you have dealt with several inverse functions. So next exercise I'm giving, you find some, some example of bijective, bijective function here. Give examples of bijective function and then find its inverse. Okay, so we are coming to now a new concept. I mean, next concept is function composition. Suppose two functions f and g they are given, right? F and g, these two functions are given. So now suppose for each x, gx is in a. See what I'm saying here. X is x is in C. C is the domain of G, not F. So suppose X is a member of domain of G, but Gx is a member of domain of F. So that I want to mean. Now, if it is so, then I can get f of g of x, right? F of g of x I can get, because by applying g over x, I can get gx, an element which is actually an element of domain of f. So I can apply f. Suppose hx equal to f of g of x. Now if it is so, then we call it function composition. So here I am getting a new function h, but how I'm getting? I'm getting it by composing two functions, f and g. So we there are two ways of representing this function composition. So f of g of x is the one way. Another way is f small o g. This o means the composition is the operator. We are composing, f and g. Okay, and so after composing these two functions, I'm getting a new function called h. This h is called composite function. So take an example. The pictorially I can show you what I've said. Suppose so from the left diagram and middle one, so left circle and middle circle and right circle. So G is defined from C to D. Say first set is first circle that represents a set C, and the next one is say D and A both. So now, after applying G on an element of C, I can get Gx. Then on the Gx, I am again applying F. Then I am getting F of G of x, right? So serially, I am applying the functions. First G, then F. And then what I get actually, so I can get as if I am jumping from x to f of g of x. So I'm getting a new function h, which is nothing but f compose g, right? So this is the pictorial representation of this function composition. So here you understand in f compose g, the domain is C and codomain is B, right? Here, if we do f compose g, then domain is C That is the domain of G, is the domain of F compose in G, and codomain is B, which is actually codomain of F, right? In this way. Now, let us ask this question. Is f of gx is equal to g of fx? Can I arbitrarily compose these two functions? What do you think? See here what I've said. First we apply g, then f. What will happen if I apply first f, then g? Well, take an example. Suppose fx equal to 2x plus 3 and gx equal to 3x plus 2, and consider both are defined on set of naturals. Okay, x and x here, so consider there's x is a natural number. Then f of g of x I can get. So gx is actually 3x plus 2. So f of and f is 2x plus 3. So doing this, I get f of g of x equal to 6x plus 7. Now find out g of fx. Then I get 6x plus 11. So obviously they are not same. So f compose g not equal to g compose f in general. Sometimes they may be equal, but in general they are not same. So therefore, how I am applying the functions, that matters. The sequence of application matters. So therefore, function composition is not commutative, right? And what more I get, what I understand from this function composition, this is a serial operation. As I've said, that I am applying the functions in sequence. Suppose h equal to f to the power n, same function. Okay, to make it simple, consider I am applying same function again and again, again and again. So say n equal 2 means h equal to f square, f square. What does it mean? First you find fx, then f of x, right? So I am applying n time this f. So h becomes h equal to f to the power n, right? And here f is applied one after another. Now, why we need function? Function does something, right? Function, it takes some input and gives some output. It does some operation. It performs some task, right? That task is performed here, you know, sequentially, one after another. See, I can give several examples in my slide. I have not given an example, real life example, but to do some task, we sometimes divide it into several subtasks, right? In other words, so there are some subtasks. By performing those subtasks, we perform some task, right? So if I consider that performing this task is a function, then how I can perform a task? That is by performing those subtasks one by one. Finally, I can we can be able to solve the problem or perform the task, but that is done by applying one by one. So in function composition, there is a sense of serial operation. There is no parallelism. one, first one, second one, third one, etc. And as I've said, now daily life, and and in our when we deal with computing also, we find we can do several things where these small functions are applied serially. Question is, what if I apply the functions parallelly? So, with this question, we move to the next concept called parallel map. And in this era, in the era of high performance computing, parallelism, you know, uh, uh, is a basic property, right? Although we can perform many tasks serially one by one, but in many occasions we love to do those tasks, you know, in parallel. Okay, so let us study that problem mathematically. Well, so what I have considered here, f is a function, and we are applying f in parallel. How I'm doing? So think this figure. Say f is there. Say n number of f's. Small circles. They're actually the domain A of f, right? And they're same actually. So I am applying this f parallelly, right? What will happen? I can get a set D by this A. So the outer circle of left side, not circle actually, outer shape. Hmm. Uh, Outer oval shape, you can say, that is the domain. I am calling it, say, D, and D, I am getting this D by A. I'm not saying what is the logic of getting D now, but okay, I'm getting D. You understand from the figure that I'm getting D by A. Then I can get a function G from D to C, right? The property is, what is the property? Property is in G, the function f, small f, they are applied parallelly on the members of D. Members are, subset of D, you can say. This is called parallel map. On the contrary, just we have seen before, what I have seen? I have seen that, say, first F, then G, or then NF, so F, etc., F to the power N. So I first find fx, then f of x in this way. So when I get f of x, the outer f waiting for fx value, right? Because serial operation. But here nobody is waiting. So all are working parallelly, right? So in this way, I can get a set, I can get a function capital G. Okay, this is a parallel function. We call them parallel map. So here G is the actually name of function, and D is the domain, and C is a codomain. Take an example. Suppose D equal to a to the power n for some n. It is a natural number, right? In my course, in the whole course, when I say small n, if not defined otherwise, n is a natural number. Then suppose this is my gx. how I'm getting this gx? So the subscript fi, you can see, means I'm putting restriction. I can get gx. Gx is an element of c. I'm putting extension I. So I is a value. So 1, 2, etc. That how I receive that one? F of xi. Okay. Uh, this bar indicates I am putting restriction. You can think that okay, these a n times a. First location is location number 0, then location number 1, then location number 2, then location number 3, etc. In this fashion, you can think, right? So that I'm talking about. G of x putting restriction on I is equal to f of x. Now here is obvious result that if f is injective or surjective, then G is also injective. See in the figure, in the right hand side figure, in the D, so the domains of A, there is some interaction, some overlapping is there. But here I am considering there is no overlapping. Suppose I am considering there is no overlapping. So as if you are calculating f of x for some x and they're putting together. Now if f is itself injective, then G, which I get out of this f by putting together, that has to be injective, right? Similarly, if G is injective, f is surjective, then G is also surjective. Okay, so ask me question if you have any after the presentation. If you have any problem with this result, I am claiming that here if f is injective, then G is also injective, as well as if f is surjective, then G is also surjective. But now take another example. Now consider, make it more simple. Suppose a equal to 0, 1 and f is, so I'm defining f a different way. Say f is a cube to a. I mean, if f is having of 3 arguments. So if it's a binary function, you will understand because a is 0 and 1 and a is 0, 1. So if it's a binary function, it takes 3 argument. So a cube to a. And suppose d equal to a to the power n. Now how I am defining gx here? So each element of x of gx is calculated in this way. It is equal to f of xi minus 1, xi and xi plus 1. I mean that if you consider a function in the ith position from the first position to the ith position, so like this one. So and then how it is for how we are finding out, see, f, that f takes xi minus 1 and xi plus 1 apart from this x. You can consider as array of d stored in an array, right? D stored in an array, and x is 1 bit sequence of the array, right? I'm finding gx, means I am applying this f on every position of the array. So at ith position, what I can get? X of I, and it is taking, suppose it is taking the other argument, say xi minus 1 from xi minus 1, and the next other argument from xi plus 1. So in this way, I am defining. Here one thing is obvious. If this is the case, F cannot be injective, right? F cannot be injective because say A3, okay. So in the domain there are 8 elements. So 0, 0, 0, 0, 0, 1, 1, 1, 1. There are 8 combinations. Small f, they are mapped to say 0 and 1, so it cannot be injective. So f is not injective. Can G be injective? In just previous slide, we have seen that if G is if is injective, then G was also injective. Okay, but here my definition of G is a bit different. I'm considering some overlapping thing. Can G be injective? Take a some special example. Suppose this is my f. So f is x, y, z is always 1 minus x. So if x is 0, then f of x, y, z for any y, z, it is 1. And if f is 1, x is 1, then f is 0. And suppose n equal to 4, right? So consider this one. Then the previous idea will be clear. So I have stored the value of the d sorry sorry in this array. So it's an array 0 1 1 0, right? Now f is applied on every location. There are 4 locations, so I am applying 4f, same copy but 4 times I am applying them parallelly. So red marked position is there. So if it is red marked position, then what I'm getting? So it is 0 1 1. So x is 0, y is 1, z is 1, as I have defined f x y z equal to 1 minus x. So here what is x? X is 0. So f of 0 1 1 is equal to 1. So see that I have written here 0 1 1 0 from this 1. So red mark, look at this red mark location, red mark bit, it was 1. Then again the after applying this function, it remains 1. Why it is so? Because f is like this one, f of x y z equal to 1 minus x. Consider the next cell. I know sorry, consider the next position, next one actually, right hand side 1, it is 1, but now it becomes, here it becomes 0. Why it is so? Because here you see f x y z, here x is 1, red 1, then next one is y, and 0 is z. Now if you consider if apply f here, so by the logic f is 1 minus x, so 1 x is 1, it will be 0. So next bit, next one, it becomes 0. So here we are applying this f parallel. And interestingly, there is a overlapping relation, right? So domain of one f is being changed by other, right? And see, one interesting you can notice here, you may ask this question also, that it is n equal to 4. What about the first cell and last cell? So leftmost cell, it was 1, it was 0, I made it 1. And you may ask that, okay, it was 0, but there is no minus 1, minus, there is no x. But here what I've considered the array as a circular array. Okay, the circle I have considered. So this is this you can consider. For the time being, you consider that assume this one. The array is circular. The array where I am storing, this value of d, this is circular. So if it is circular, then x is 0, y is 0, z is 1 for the first cell I'm talking about, for the leftmost cell. So it is 0 0 1 I am getting. 1. Similarly, for the rightmost cell, it is 1, then 0, then 0. So, so x equal to 1, y equal to 0, and z equal to 0. So 1 minus x is 1, so it is becoming 0, so 0. So after applying this one, after applying 4f parallelly to these 4 locations of this array, I am getting 1100 from 0110. So this G is the parallel map. We call this G as parallel map. I think resonance is obvious. Now let me ask this question. What I've asked just now. Is this F injective? You please test. I shall ask you right now that is this G injective? So how can I find this one? Since n equal to 4, you can get only to the power 4 combinations. So all 0 to all 1, right? For all 0 to all 1, if your d equal to the power n, so your d equal to the power 4. So combinations, bit strings, all possible bit strings of length 4. It's all 0 to all 1. So you find out, you test for each one 00040, then 0001, 0010, etc. For each one, you find the next one, applying this logic, what I just said, and then you test if it is injective, declare it is injective. If it is surjective, declare it is surjective. If both, declare it bijective. But you have to do it. So here, 2 examples I have given. When we are defining parallel map, I have given 2 examples. One example, this global map, sometimes we call it global map, this parallel map is sometimes named as global map. So G has just used F 1 by 1, and F takes an element from its own domain and then find Fx. For that case, I claimed that if small f is injective, then G is injective. That is simple case. But case becomes difficult, a bit difficult, if we see that domains overlap. The example I've given here, another example in the slide, what you are seeing here, it is difficult, comparatively difficult, than the previous, because overlapping bits are here, right? As I have shown in the figure, in the right hand side figure. So domain of one function is overlapped with the other, right? So in this case, so the answer is not trivial. Interestingly, the example in this example, A is not injective. It cannot be injective. If it is AQ to A, it cannot be injective, right? In general, I mean, you understand that size of domain is less than size of codomain. It cannot be injective, right? It's a general understanding. So A cube, there are 8 elements, 0, 0, 0 to 1, 1, 1. And it has to be mapped to only 0 and 1. It cannot be injective. So the question comes, can, instead of this fact, can G be injective? So this is not trivial case. The example I have given here. Now, if n is finite, then it is doable. As I've said, the example I've given you as exercise, you find all possible, all 002, all 02, all 1, you test and then decide. But the challenge is, suppose if is applied infinite times, then what will happen? Then you cannot do it manually like previous, like the example, like that's an example. You cannot do it by paper and pencil or by writing code. Question is, can we decide injectivity or subjectivity of G? I can give you F, and I shall tell you that F is applied infinite times. So D, the domain of G is actually infinite set. In that case, can you decide injectivity? So this is a great challenge. This is a great challenge. When we deal with parallel computing, parallel processing, etc., then normally we don't deal with infinite case. So not normally, but always we don't deal with infinite case. So always f is applied finite number of times. So it's all, if it is applied finite number of times, it is always decidable. You can always decide. Maybe you need more time, but you can decide it. But theoretical challenge is, if it is infinite, can you decide? So in this course, we shall address these questions several times, right? F is applied infinite times, but we shall try to decide injectivity and surjectivity. And we shall see some amazing results. Although in many cases, injectivity and surjectivity cannot be decided, but there are some cases, a good number of cases, where we can decide injectivity and subjectivity of this kind of parallel map. So that's all for today. What I'm saying, that I have given you two tasks, so two or three tasks. So you do it and let me know your response. And first ask questions if you have. Prithviraj, yeah, please. Shupriti,
Sir, you said that what was that?
which one?
Relation and no, the relation and mapping are same. Actually, it's sorry, relation, not relation. The function and mapping are same in literature, but you said in set theory or something they are not equivalent. And which one came earlier that I mean I
Okay,
could not
no,
hear that.
function mapping, the term mapping is used in set theory. Set theory, we use the term mapping generally. But function, it is 1,000 year olds concept.
Also, function is earlier. I
Yeah,
mean,
yes, yes. Function is much earlier. Huh.
okay.
So Newton, dealt with functions, and the calculus, everything they are developed based on functions.
Hmm.
Before that, Al-Khwarizmi first, the great Persian mathematician Al-Khwarizmi, he worked on functions, several kinds of functions. Okay, so it's older than this. Mapping concept is newer.
Okay.
Yes. Any question?
Sir, can we get PPT, sir?
Yeah, you can get PT. You can get this, this video also, because I've recorded this one. You can get the same. But
Okay, sir.
you have question, Prithviraj, you have question?
No, sir, I have a like concept doubt in the parallel functions, but I'll get it, sir. I'll get it myself.
Uh,
If I
uh,
have any doubts, I'll ask later.
So actually, I couldn't prepare more slides. When I was saying that, I realized that okay, there are few more slides are needed here, especially this case. But
Yes,
I
sir.
think when I gave this example, the last example, if you look at the example, then the previous concept will be clear. So
Yes, sir.
you do it by your hand. Hmm.
Yes, sir.
Is it clear? Can you see, Prithviraj, this one gx equal to this subscript I? What does it mean?
Yes, sir. Yes, sir.
So uh, if it is clear, then I can tell you a few more. Should I explain it more?
Yes, sir.
So okay, let me use the board now. So I don't have just a sec, just a sec. Can you see my board?
Yes, sir.
Okay, I'm saying what I've written there, that g of x restriction I have put, and f of x I. Na? So actually,
Yes, sir.
suppose x equal to say 0, 1, 1, 0. Say n equal to 4 I have taken, right?
Yes, sir.
So this is a location number. So this is, if I consider it's an ordered one. So this is the first location, second location, third location, fourth location, right? In this way, I can number.
Yes, sir.
So x 0 means I want to means this bit 0. X 1 means this one. Similarly, x 2 means this one, this bit. So this bar means this one. X3 means 0. Means I'm putting restriction. Means from this one, 0, 1, 2, 3, for this 4 bit, I am extracting this one, third one, right? So now here, if I do gx here, right? Then also g of x, it will have this 6 on 4 number of locations. I am
Yes.
extracting the ith location in a similar way. Now, suppose, for example, gx is equal to say 1, 1, 0, 0. So then g of x 0 is this location,
Yes, sir.
right? G of x 1 this location, next location. Oh, sorry, this is 1 actually. This is 1. This is 1 in this way. Huh. So what I'm saying here, what does it say? That I am getting this, say x1, say g of xi by just applying f over this xi. Okay. So actually, what is the meaning of this? That g of x actually nothing but in this particular example, what I can get? I can get actually gx is equal to f of x0, then f of x. So I'm not putting comma here, so you understand. Then f of x2, then f of x3, right? So I'm as if I'm putting placing them side by side. So that is the meaning of this one, this meaning. But for the second case, in second case, what I've said? Second case, I have said that g of xi, how can I get? Second case I have said you take I minus 1,
f of xi minus 1.
then xi, then x of I plus 1. Then means you take, for this one, you take the previous one, this one, as well as this one as input. So I'm making independent, right? The example,
Yes, sir.
yeah. So, as example, I have taken 0, 1, 1, 0. In the slide, in the PPT, I have given this example. Suppose this f I apply. So it is taking these three argument, left, self,
Hmm.
right. It is I minus 1. It is I. It is I plus 1. Then I'm getting 1. And for the this right side element also, I'm doing the same thing. I'm applying f here. C is overlapping. This is the domain of f, this f, left side f. This is the domain of right side f. See, these consecutive ones, they have overlapped, right? For this f, it is taking this to one, and for right side f, another two one it's taking. So this kind of overlapping makes situation complicated, right? And that's a challenging one in case of parallel mapping. Okay.
Okay, sir.
Any more question? I'm saying here Vicky, Vikrant. Vicky, you were from NIT Trichy?
Yes, sir.
Okay. Kamalika has referred you, na?
Yes, sir.
Professor Kamalika Bhattacharya? Yeah, okay. Okay.
Sir, I have a question.
Yeah, sure.
Sir, as you told you that in function composition,
Yes.
that fog is not always equal to buff. So, if
Yes.
in case FOG value is equal to GOF value, so is any possibilities?
I'm not getting your point. Please repeat. So you have said F O G, F compose G, and G compose F.
Yes, sir.
They are not always same. Yes, not always.
Not always, no, sir.
Yeah, not always.
Okay, sir. If in case it is equal to buff value, then uh, is there an inverse is possible? Inverse.
Whether inverse is possible, that depends whether it's bijective or not. This is the only condition.
Okay,
If they're same, then you have to test whether it's bijective or not.
okay. Thank you, sir.
Okay. Well, Parajat, do you have any question?
Not
No.
really, sir.
Okay. So I shall take the next class from 11, on Friday, coming Friday from 11, right?
Okay, sir.
Okay. Okay.
Okay, sir.
Okay. And as I've said, maybe in the beginning, I also said that this Monday class may be shifted, say after say 2:30. That will be notified through this, that one. Uh, and Vicky, have you filled up that the form?
Not it, sir. I will fill.
Okay, you fill up it, then I'll get your Gmail ID, then or your email ID, and you'll be invited accordingly. Okay.
By the way, sir, while I was trying to fill up the form, what have we have to fill in the affiliation section? Like there was a section called as affiliation.
Your
What we have to
IST?
write?
You have IST?
Okay, okay. Yeah.
Yeah. Okay. So now I'm leaving.
Thank you, sir.